Now we're ready to talk about integration techniques. Let's start with one called U-Substitution. First, I want to recall the chain rule. So the chain rule we use when we're differentiating a composite function, so the derivative, say, of f of g of x, and that gives us f prime of g of x times g prime of x. If we then integrate both sides of this expression, this says that the integral of the derivative of f of g of x is equal to the integral of f prime of g of x times g prime of x. And finally, that left-hand side we can simplify. We're saying here that the antiderivative of the derivative of that function is simply itself, potentially plus some constant, so I'll include that. And so that is now equivalent to the right-hand side. So this is what we get here. And when we're using this, we're really going to be thinking about starting from that right-hand side. The hope is that we can then unravel that to get what we have on the left-hand side. So where does the name U-substitution come in here? What we can do is let u represent g of x. So u is a function of x. But in my shorthand notation, instead of writing u of x, I'm just going to write u. Then that means that when I'm talking about du, that's going to represent g prime of x dx. So I start with this assignment. Then the way we'll use this is if I start with the integral I have on the right-hand side in the boxed expression, the integral of f prime of g of x times g prime of x, I can now refer to that as the integral of f prime of u du, given the assignments above. And again, the antiderivative of the derivative of f is simply f of u, potentially plus some constant. And then we're going to see the important thing is if I start with an integral with respect to x, I want to end up with a function of x as well. So I replace u with its equivalent g of x. So that's where the name comes from. To see it in use, consider the following example. We're looking for the integral of 2x sine of x squared. Now, part of what we'll develop in the next video is some experience and some intuition about when to use U-substitution. But for now, I'll say this is a classic example where we can, and we'll end up seeing kind of what to look for so that I know to use that technique in the future. Now, once I decide to use U-substitution, I'm looking at the integral, and my hope is that I can view it as representative of what I'm underlining here above. So we need to look for a choice of what u should be, and we can see that it's kind of nice if perhaps that function u has its derivative represented in the integrand as well. Later we'll see really a constant multiple of that derivative would suffice. So with that in mind, I'm going to choose u to be x squared. And then du would consequently be 2x dx. So if I look at what I have here, my 2x dx, I'm saying now I can replace with du. And the sine of x squared is now going to be equivalent to the sine of u. So this substitution says that starting with the integral of 2x sine of x squared, I can rewrite that as the integral of the sine of u du. So now I'm looking for an antiderivative of sine, which I can express as minus cosine of u plus c. And like I said earlier, importantly, we're not done. I want to express this as a function of x, which I can do if I replace u with x squared. So now we've found our answer using that technique. What I do want to point out before we finish this video is we have to be a little bit careful with definite integrals. And the confusion comes in because you have the variable x and the variable u, and we need to be very clear about what our bounds are actually bounds on. Are they bounds on x or on u? So to emphasize that, again, I'm going to take the same integrand we just saw, but I'm going to look at it for a definite integral. So we want to look at the integral from 2 to 3 of 2x sine of x squared. If we were starting this problem from scratch, the first thing I would do is the work we did above. I would identify u equals x squared, find du, and start to rewrite that integrand. So I'm going to take advantage of the fact that we've done that above. And so I'm still thinking that u, when I reference that here, is x squared. So I want to look at two different approaches here. One I'll refer to as method 1. And here, what I'm going to do is, once I've defined u equals x squared, I'm actually going to find out what the bounds on x imply about the bounds on u. So if x is 2, u is 2 squared or 4. If x is 3, then u is 3 squared or 9. So the integral we started with, that from 2 to 3 of 2x sine of x squared, can be written as the integral of sine of u du, like we found above. And here I can write from 4 to 9. So the indication here is that I'm saying that I'm integrating with respect to u, so those numbers now represent bounds on u. I would find the antiderivative like we did above. Here I'll leave off the plus c, and I'm going to integrate this from 4 to 9. And that's going to leave me with minus cosine of 9 minus a negative, or plus cosine of 4. So this would be my final answer, and we saw one way of getting here. Same example, just what I'll refer to as method 2. So in method 1, we rewrote the bounds so that they bounded u. In method 2, what I'm going to do is keep the bounds on x and then revert my final answer back to a function of x in the end. So we're going to get the original integral, rewriting that once again as the integral of sine of u du. Now, if I just wrote from 2 to 3, that would imply that those are the bounds on u. So I'm going to write from x equals 2 to x equals 3. And that reminds me that I need to reconcile these different variables. So the antiderivative is, again, minus cosine of u, and I'm evaluating that from x equals 2 to x equals 3. So I'm going to rewrite that now as a function of x, minus cosine of, and we said u was x squared. Now I can simply just write 2 and 3. Those are the bounds on that variable. And notice that I get the exact same answer. I get minus cosine of 9 plus cosine of 4. So these are just two different ways to deal with the fact that we have two variables and being careful about our bounds. I will say either is fine. I have a slight preference on the first method. And that first method, I think, does make it easier to solve some of the more symbolic problems. So when you're working through the textbook problems, you'll find some of those near the end of the section are less just solve this integral and more you have to think about the pieces. I often find that reverting your bounds into the new variable can actually be very helpful in those.